This video is to introduce the concept of event interval probability analysis, or EIPA. This is a new data analysis method that's designed to look at event intervals and to develop probability values associated with those event intervals. We form a null hypothesis that there are no trends in the data and use probability values or p-values to reject or not reject that null hypothesis. This is the scientific method at work. And currently, for commercial aviation crashes, neither the commercial aviation industry or the FAA is applying any science to evaluating those intervals. This video is in part intended to make sure that the commercial aviation industry, the FAA, uses event interval probability analysis in their decision making in the future. My name is Jan Smith. I'm a professional engineer, a reliability engineering consultant with 56 years of experience in reliability engineering on repairable systems principally in the process industries. The first technical paper, peer-reviewed paper, was published in 2018, and it was directed at the process industries. But since then, the last 4 papers have been devoted to applying it to the commercial aviation industry and applying it to the number of departures for the fleet, the number of departures to the first crash and the number of departures to the second crash and so forth, and applying it to crash intervals and also precursor intervals, those less serious events that can alert us to an unreliable aircraft even before the first crash. Now, this video will include part of the built into the video is a description of a Microsoft Excel workbook. One of the sheets is what we call a probability map. It's a way of organizing the numerous interrelated equations so that we can see probability values and their trends and readily, and to see where we can, based on probability values, reject that null hypothesis and say, yes, there is a reliability degradation in our system. And so there are 3 data sets that we will use in this video. The first is a simple process pump with a time between failure in days. The purpose of that is to demonstrate the concept and the methodology so that we can understand it, because when we go to looking at one event, for example, on the last 2 data sets where we look at crash intervals and precursor intervals for the 737 MAX, we will see how the process works even with one event. And so we will be able to do a complete probabilistic analysis based on one failure. And that's something that has never been done in the past. So this is a new method. And the FAA and the commercial aviation industry in particular need to pay attention and to use this methodology in the future. Also, the fact that they haven't used it in the past is no reflection on them. This is not being taught even to reliability engineers who are receiving degrees in reliability engineering. So the academic community is encouraged to develop this data analysis methodology into the curriculum for engineers. Now, I've mentioned we're applying this to engineered systems, and it doesn't have to be engineered systems. We will see that this can be applied to business systems and to systems that really aren't systems at all. They might be abstract systems. In a later video, not this one, but in a later video, we'll talk about where we have actually implemented, done this on industrial injuries, and the number of industrial injuries where the interval, the domain over which the intervals are counted is man hours worked. And so there isn't a system that develops industrial injuries, of course, but we can treat that as an abstract system. For that reason, this data analysis method is applicable to social and natural sciences, business systems, not just engineered systems, but these three data sets that we will cover in this video will be on engineered systems. These are the technical papers that are available from these technical societies, or shortly will be available, or they can be downloaded from pmfseries.com. Also, the spreadsheet that supports EIPA can be downloaded free of charge from this website, and it is macro free. I want to point out how the terminology has changed over the years. In the 2018, the first paper, we called it failure time analysis, and when we applied it to the 737 MAX, the first paper, in January 2020, we called it failure time analysis. But because of the broad applicability of it, it's valid for things other than failure time. So we now call it event interval probability analysis, or EIPA. The papers 2, 3, and 4 applied the analysis method to aircraft crash events. And the latest paper, recently presented at the January 2022 RAMS conference, applies it to precursor events. All of this data for papers 1 through 4, this data was used, or the analysis was used, using estimates that were conservatively estimated. And by that I mean estimates that underreported the significance of the findings, not overreported. And so this video uses updated input data for the analysis and demonstrates that the analysis method is even more sensitive than reported in these 4 papers. And the end result of this is that had we applied EIPA to crash intervals, we could have saved hundreds of lives over the last 75 years. And if we applied it to precursor events, we could have saved an additional hundreds of lives over the last several years. And this is looking at reduction in fatalities. And when we recognize that the 737 MAX not only caused 346 fatalities, but tens of billions of dollars, this is a method that it needs to be paid attention to, and it's applicable, so broadly applicable that I think this will be obvious as we go through this video. And so now we'll get into looking at the probability map. This is a Microsoft Excel workbook that's macro free, and it can be downloaded from our website. We have to have a tool such as this to structure our data to make the analysis practical. And I think the structure of the worksheet also allows us to understand the concept. So let's go to a sheet called various data sets, and you're probably interested in the 737 MAX that we're going to get to, but the concept cannot be understood and accepted if we are using only one event or 2 events. It's too special purpose. So we're going to start with a more general data set that allows the concept to be developed before we jump to the 737 MAX. So this is process pump time between failure data in days, real data from the petrochemical industry. So we're going to copy that and place that into this green region. We'll maintain formatting, and the cells, that the formulas that are in the cells in this sheet as well as these other sheets draw upon this data and begin the analysis. So what we have here are some rows that are hidden because we're going to be scrolling between the 3 sections of the probability map and the hidden rows allow that scrolling to be easier. There are some empty cells, and this simply is to give us a working range for our data set. Most data sets would fall perhaps within this working range. Because we have empty cells, we are generating some error messages as well as some junk numbers due to empty cells. We don't want to be distracted by that, so we cover up this image, and this image will also be helpful when we evaluate one row at a time. Our analysis is one row at a time, and that'll be clear as to why that is as we go along. Let's explain the column headings. The first column is empty, and that is simply for ad hoc calculations, and we'll be using that later. The event number, the first event occurs, the second event, and the analysis is conducted contemporaneously upon the arrival of the event. So the data set is developed. At this point, at event 3, the data set consists of 3 values, and then the data set consists of 4 values, and then the data set consists of 5 values, etc. So each line is developed using only that line and the data that is above that row. The time between event, the event is failure, in failures in this case, and the time is time between failure and days. The interval over which we count the events does not have to be time. It can be any other interval, and when we get to the 737 MAX, for example, it will be departures or flights or cycles. The MTBE is simply the running average for our data, and the columns shaded in gray have to do with Laplace trend test p-values. The cumulative TBE is simply the cumulative of this data set. And the cumulative TBE serves a couple of purposes. It's a helper column for the somewhat complicated Laplace trend test p-value. Helper columns are normally hidden, but there's a traditional way of plotting data that some may want to use, and that is to plot cumulative TBE on the x-axis, the cumulative event number on the y-axis, and deviations from a straight line are indications of possible reliability growth or degradation. All these numbers are p-values, probability values, and as these numbers approach 0, they are increasing strength of evidence that there is a reliability degradation in the system that generates these numbers. And as the numbers approach 1, it is increasing strength of evidence that there is a reliability growth in the system that is generating these numbers. So the Laplace trend test p-values did not pick up any indication of degradation in this system. And we think we see degradation because of the last 4 failures are short relative to the prior average. So we think we have a trend here, and the p-values are intended to pick up that trend. So we don't see it with the Laplace for this data set. We will see that later. But the values to the right of this black dividing line did pick up this, what looks like maybe a step change, and in our data. And these are Poisson probability values, and I'll have to explain why we can use Poisson. I think the conventional wisdom is that we can't use Poisson because Poisson can only be used if there are no trends in our data, and we think we have a trend. The Poisson probability is applicable when this is derived, these numbers come from a homogeneous Poisson process, which means there's no trend. the numbers have to be, the values have to be identically and independently distributed exponential random variables, which means no trend. So on the surface, we can't use Poisson to look for trends. We can use Poisson only if there are no trends. But we are using Poisson in something of a reverse fashion. We are forming a null hypothesis that there are no trends in the data and using the Poisson probability to evaluate that null hypothesis. And the scientific method, this is the scientific method at work. We form a null hypothesis and we reject that null on the basis of p-values. So these low p-values that are shaded red, thanks to the conditional formatting that is embedded in Excel, this helps us to identify the location of the p-values that indicate reliability degradation. And so let's talk about the PV1, PV7. What does that mean outside the context of EIPA? You haven't seen that, I don't suppose. So let's discuss some of these, a couple of these, and you will understand them all. PV4, P-V4, that stands for probability value 4, or P value 4. And let's describe what that means. There are several of them for this data set, and so we have to link, to understand one of them, we have to link it to an event. So at event 13, for example, let's look at this p-value 4 for event 13. And let's describe in words what is in that cell. What is in that cell is the answer to this question. What is the probability of 4 or more failures occurring within a look-back period of 4? So a look-back period of 4 is the sum of events 10, 11, 12, and 13. And when this is the time period we're evaluating in this cell, we use the mean for the data set at the event that we are evaluating. So using Poisson probability, we get a value in there that answers the question, what's the probability of 4 or more within a look-back period of 4, and the mean is that at the event being evaluated. We are not going to get into formulas in detail because I think you would probably know the Poisson equations that would be in these various cells. And you can stop the video and assess some of them if need be to get a better understanding. Let's describe one more of these column headings just to make sure that we understand it. Let's look at PV1 at, let's say, event 10. What is in this cell is the answer to this question. What is the probability of 1 or more, hence the 1 or more events occurring in a look-back period of 1 when the mean is that at the event being evaluated? So that is the Poisson formula that is in this cell is intended to answer that question. Let's look at the values that are in some of these cells. The lowest number that we have on the screen is this PV4 at event 13. It says that there's 2 chances out of 10,000 that we could have these 4 quick events occurring with a system with a mean of 365 when there is no trend. So it means that would be an exceedingly rare event. So using the scientific method, we reject the null hypothesis and we say, yes, there is a trend in the data, we need to investigate, do a root cause analysis, whatever's necessary to correct that trend. Otherwise, we might have failure event number 14 quickly. But that is unnecessarily strong strength of evidence. PV3 at event 10 with an 18 chances out of 10,000 that we can have those 3 quick failures when the mean is 395 and it be from a system where there is no trend. So we reject the null hypothesis. PV2 at event 38, there's 5 chances in 1,000 that could occur by random chance when there really is no trend in the data. But that's really strong strength of evidence, stronger than necessary. We trace our low p-values back to event 10, where the first opportunity to identify a degradation is the very first event very first low TBE value at event 10. We see that there's 17 times out of 1,000. This could be a no trend system, and we can have a value as low as 8 when the system is 466 for a mean. 17 times over 1,000. This could occur simply due to randomness in our values, but that is sufficiently low that we can reject the null and say, yes, there is a reliability degradation. Despite limited data and only one short event, we can make that determination. And so we reject the null. What it means is that for this particular pump, what we would do, what should be done, is to get this data the day that the event occurred, right after the event. Sometimes we have to react almost in real time, but depending upon the system, we would get this number the day that the pump failed, or possibly the following day we would get this number. And based on that low p-value, we would investigate to see why the degradation in the system. Depending upon the economics, the safety, the environmental ramifications, it might be a root cause analysis, or it might be a simple investigation. But the correct set of eyes on the basis of criticality and economics and these other factors, we would get the right people looking at that. Maybe it's if the economics are low and there's no safety and environmental aspects, it might simply be to alert the repair crew that the equipment may not have been repaired as good as new upon the last repair, or there may be something changed in the process. Perhaps it could be as simple as a level instrument in the process that is drifted out of calibration, affecting the process that the pump is operating in, which could lead to something like, well, for example, cavitation of the pump, which severe cavitation can certainly lead to degraded reliability. So any number of ways, certainly beyond, we have to look beyond simply the physical pump itself to the environment that it's located in, and the operating and maintenance procedures under which it is operating. Perhaps there's been procedural changes, or we haven't adhered to certain procedures. Any number of reasons why we may have a low number, but we evaluate as though there has been a drop in reliability, and we do so based on this probability value. So it's the probability value that raises the first awareness that there may be a reliability degradation. We do that because we can't look at every failure on every asset that looks like it might be maybe a short duration. Our limited resources would be too unfocused, and so this allows probability values allows us to focus on what is true issues as determined with probability values. The 0.017 that probability is also a measure of our false positive. We could be evaluating this event 10 when indeed there is no trend in the data, and the 8 is simply low due to random variation of a system that is as reliable as it always has been. So the 0.017 is a measure of that false positive. So when we do the analysis, we keep the false positive in mind. Now, another interesting thing is that we are making a decision on the basis of limited data and one quick event, and so we may want to consider the fact that this 0.017 is not a single valued number. This false positive, there's actually a distribution around this p-value. We'll get those distributions using the second and third portions of the probability map. But that distribution is also a distribution of the false positive. So when we're looking at situations that have economic or safety or environmental aspects that are significant, we may want to evaluate that false positive distribution, and we'll do that in a moment. Now, why do we have distributions around these numbers? Because these numbers appear to be single-valued numbers, but we have to keep in mind that this is a sample of a pump system that has an unknown mean. This mean of 466 at event 10, that mean is the mean of our sample. It's the mean of these numbers. But these numbers are a sample from an unknown mean. So if we could resample, we would get a different mean. Now, there are true, or maybe probably are true ups and downs in reliability in this system over, the 13-year period about that these TBE values sum to. So there are true ups and downs and maybe periods of stable operation. We think we might be able to see them here, but they may or may not be what we think they are. But even if they're true, they're unknown. And superimposed upon all those true but unknown periods of operation, different operation as far as reliability, different reliability characteristics in this data set, which are all unknown, but superimposed upon all that chaos is random variation. And we're trying to separate the random variation from the true changes in reliability in the system, and we're using probability values to do that. So if we resample that pump, we can't. It's physically impossible, but if we could, we would get a different set of numbers. Even if we could duplicate those true but unknown periods of true reliability, growth, and degradation, and stable operation, if we knew them and could duplicate them, we still would get a different set of numbers due to random variation. So what we need to do is to resample, but we can only resample using computer simulation, Monte Carlo simulation. You can't resample in real life, but we can resample that data because we have the opportunity to get an infinite number of samples because we're sampling our null hypothesis. And our null hypothesis has in it an infinite number of samples. So we will resample using a bootstrapping type of technique and get a probability distribution around our MTBE values. Our Poisson probability values draw upon the mean. So every time we get a new MTBE value that is sampled, we will get a number of probability values that are different because we draw upon this sample. So in the second section of our probability map, we will look at getting distributions around MTBE. We get mean time between event in the second section of the probability map in this region. These are MTBEs as a random variable. When we hit Shift F9, we'll see that these are indeed a random variable. They recalculate every time we recalculate in the computer. Now, where do these so because these numbers are changing, let's look at event 13, the MTBE. We have 460, and we recalculate, we get 429. We recalculate 460, recalculate 363. We can form a probability distribution around these values. But where do these values come from? The MTBE as a random variable is the average of these 13 time between event samples. And so the average of these samples will be 363 here at the bottom. That's the value here. Every time we recalculate, we generate different values for the TBE samples. We're getting 13 TBE samples because the data set is 13 at that point. At event 2, we're only getting 2 TBE samples to get the mean at event 2 as a random variable. Let's see how do we get these numbers? Where do these TBE samples come from? And there's an image off screen that will help in that regard. So what we have is that we are resampling our null hypothesis. The null hypothesis is that the system is a homogeneous Poisson process. From reliability theory, it means that this equation holds for our null hypothesis. Our null hypothesis says that for a system, a complex system that is steady state as far as reliability is concerned, then this is the reliability of that system that is behaving like a homogeneous Poisson process and has a constant lambda. When lambda is constant, we can replace lambda with 1 over MTBF in this relationship. Now, 1 minus reliability is unreliability, and unreliability is the time to failure. So if we set this relationship equal to a random number and solve for t, then this relationship here, where time is a minus MTBF times the log of a random number that is generated within Excel, then this is a time between failure sample. And so this relationship that is shaded is in each of these cells, all of these cells. The MTBF is the MTBF for our data sample at the row in question. So these 3 TBE values draw upon this data, upon this sample MTBF. And the mean of these 3 samples forms MTBE as a random variable. We have to get the right number of samples according to the length of our data set. At event 3, we get 3 samples. At event 1, we only get 1 sample. At event 13, we get 13 samples. So it's a bootstrapping type of method to get MTBE as a random variable. Now, we can get distributions around these, and we will very shortly. But these MTBE values are also reflected in this section. We simply reference the cells and move this data down to here. Now, for each MTBE random variable number, we get a new calculation for our Poisson probability values. All of the formulas in these cells that are shaded are exactly these, but these draw upon the data set mean. These here in the lower thirds portion of the probability map draw upon MTBE as a random variable. And so this is how we get probability distributions around our p-values. Getting MTBE as a random variable, and then using that new random variable sample to get a new sample for our probability values, which, as I've said, also are form a probability distribution for our false positives. So we now actually get those distributions in the sheet called Excel Monte Carlo results. We get probability distributions using this sheet Excel Monte Carlo results. This is a 10,000 row data table and a 1,000 row data table. We reference the cell that we want to get a distribution for here. A random variable goes there. Let's go to the probability map and let's get PV, this PV1 at event 10. We want to assess that. So let's reference that cell. We simply enter it and go to the Monte. We have to hit enter here, then go select that cell here, enter, and when we run hit F9, it will generate a probability table with values and form a distribution. Here in this one, let's reference the cell for the probability distribution around this random variable. It has to be a random variable cell that we select. Now when we hit F9, we will, it will take a few minutes and we will generate distributions. This 1,000 row data table takes a few seconds to run if this one is blank, and this one takes just a few minutes. And as we'll see, the resolution of this data table is excellent, but it takes a few minutes. The resolution here is not so good, but it's good for just learning and training and exploring your data, and it only takes a few seconds. These are the distributions. This data draws upon the column B and column D data. So what we're doing here is generating for each iteration, we're generating by way of different random numbers, generating samples of our PV1 at event 10. And we are resorting these 10,000 random samples of PV1 from smallest to largest in this column. There are 10,000 of these, and because they're generated by a random number process, the distributions are smooth, and we can query column D to get confidence confidence intervals for any level. We're set up now for 90% confidence level by referring to the proper cell in column D. Both the lower and the upper cell can be referenced. We can change this cell reference and get any confidence level, but these are 90%. So confidence levels are range from essentially 0.01 to 0.03. Very tight confidence intervals, although we only have one quick failure and a very limited length of, a very limited data sample from the pump with our unknown mean. And so this is the distribution. These are general purpose plots. So I had to reformat the x-axis and change it to a linear plot to see this properly. So because these are general purpose plots, sometimes this is very low levels, and sometimes it's or values, and sometimes it's very high values, depending upon the data in your random variable cell. So if we look at some data that has been published in earlier papers, some of the earlier papers, we used Palisades at-risk Excel add-in software to analyze the PV1 at the 10th event, and of course this is probability density versus cumulative probability, just different ways of plotting the data. And we had a lower 90% interval of 0.0109, 0.0108 close, 0.0312, 0.0312. So good convergence. This is 5,000 iterations, and this is 10,000 iterations. Excellent convergence. Now for the MTBE at event 13, let's look at that convergence, how that works. This is 1,000 row data table. You see a little bit of ragginess. Let's look at this is 10,000 iterations, and here we had for 90% intervals 218 and 546, 211 and 551. Not so close. And so for for a few seconds, this is excellent for learning and training and playing around with your data. But for real results, you'd want to use the 10,000 row data table for real data. So this tight distribution around which is also our probability of our false positive, we can reject the null hypothesis with a degree of confidence on the basis of one quick failure and very limited data. So let's go back to our probability map, and we have rejected that null hypothesis. Now that allows us to query the data set to see how we might change it. So let's look at the possibility that there is early reliability growth here, that we might be able to delete these two values and change our data set and explore the degradation a little bit more sensitively. We see a good indication here that we do have reliability growth. We don't have a distribution around our Laplace trend test p-value, but we can confirm that with a different method, a totally independent method. We did that with residual max min as a random variable. We got a confirming p-value. We're not going to get into that. That's a video of its own, but we can delete this data and move our data set up and see how that changes. Before we do that, though, let me just indicate that we can simply go to conditional formatting and change our rules so that we can see the reliability growth. That helps us to see it. Wasn't really necessary in this case, but sometimes the conditional formatting is very helpful to help you see the data. So we can delete this data, move our data set up. We have two, and of course, we see that we did have early reliability growth, and that was years ago. So we might be justified in removing those two early failures that occurred like 13 years ago, and that will make our data more sensitive to this degradation in reliability that occurred later in life. So let's change our conditional formatting rules, and you can see that if you're looking at all of these numbers, the the formatting certainly helps. So now we can see the degradation more clearly. All of these p-values drop. I think this was 0.017, that's 0.014. So the Poisson p-values drop, but the Laplace p-values dropped lowered tremendously, and did pick up the change in reliability, or a trend in the data. And the reason being is that Laplace looked at those two early events and gave them weight, just like it did the more recent events. Laplace looks at the entire data set when it generates a number such as this. But it's very, very helpful for looking at long-term trends in the data. Oftentimes, it is much more sensitive than Poisson. So, but Poisson looks for step change in the data, which we think we see here. This data looks a lot different than these two events, or these four events. So, a step change to which Poisson is very sensitive. Now, so another thing we might want to do is we measure the reliability of this pump against itself, looking for changes in reliability. And because for this pump, we may not have a large population against which to compare, but oftentimes there is a large population. We didn't have it in this particular pump, but we can imagine that there is a large group of pumps that has a parameter mean of 900. And so this is a population parameter. Not a sample from an unknown. Our data here is not a sample from an unknown mean. Our null is that it is a sample from a known mean. Another way of saying it is that our null hypothesis is that our pump is equally as reliable as the population against which we're comparing. And so when we do that, we see that our p-values work just like before, except now we don't have distributions around our MTBE. Therefore, we don't have distributions around our Poisson p-values. So one of the things when we're comparing to a parameter, here is something, and we're working our way toward applying this on the 737 MAX, in which we want to use one event and then two events. When we delete this data, we see that these p-values in this region did not change. So the p-values associated with these four events wasn't affected by being blind to any history. It's as though there is no history. Another way of looking at it is let's move this data to the top of our data set, and we'll see that these p-values here are identical to these p-values down here. So we don't have to have history against which to compare when we have a parameter, and the parameter for the 737 MAX is the worldwide jet carrier schedule fleet worldwide, and we have that value. And so now let's get the 737 MAX data and take a look at that. We'll go to various data sets, and here we have data for the 737 MAX. This is departures between events. That's the number of departures between those two fatal crashes, the first crash, the second crash, and this is the mean for the worldwide fleet, which we'll use as our parameter. In earlier papers, I have used different data, and that's because my my data sources gave me different estimates. The worldwide mean has stayed the same, but the departures between event changed in earlier papers. Now, this is, I believe, the best data that we have. The only piece of data that is estimated is this value. And when we look at precursor events, we will look at the source of this data in one of the other sheets. So we will explore why this data is what it is when we look at precursors. So let's copy this data and move it to the probability map. We paste in special values, and we want to look at of course we have low p-values, but let's look at the first event first, because we want to do the analysis like 1 hour after the plane, after we have a crash, or certainly the next day. This analysis should be done in the future. Now, it wasn't done in the past because EIPA was in its very much its infancy, and no one knew about it, and it had never been applied to something like a single aircraft crash. It had been used in the process industries only at that time. So we have a p-value that would reject the null hypothesis. It says that on the basis of that single number, we could have, and in the future want to at least consider grounding the fleet. Now, for the process pump, we talk about investigating to see if there's a problem because of this low p-value. The low p-value signals that there may be a problem, and we investigate. For aircraft, that is not too feasible, because the hour after the crash, we don't have a lot of good information about why the crash. And so this analysis method works without any cause and effect data. And so if you imagine the aircraft just going off radar over the mid-Atlantic, you don't have any data at that time. But we do have this event data, and so we need to use this event data in the future. So we would reject the null hypothesis, and we could use this data and generate a risk of continued operation. To save time, I won't do that. We'll do that after the second event. So after the second event, we have a PV1 that is similar to the first PV1. Each one of these events, either event 1 or event 2, could easily lead to grounding the fleet, because we have pointed out with these low p-values that there is a low chance that we have a plane that's as reliable as a worldwide mean. In all likelihood, we have an unreliable aircraft. Now, two fairly rare events in a row is much more unlikely to occur than each event independently. That is just common sense. And this PV2 at event 2 is sort of quantifying that common sense. We see that there's about looks like a 9 chance in 10,000 that we could have two crashes within this interval if the mean is like the worldwide mean. So very little chance of it being a reliable aircraft. Now let's do something else before we reject the null hypothesis, let's evaluate these low probability values with a different independent concept. And to do that, we are going to look at this image again, and we're going to, now we have not rejected the null hypothesis yet. We are looking at these numbers using reliability theory. I say it's a different concept, although we'll see that the mathematics behind the concepts are identical. I say that they're independent because if Poisson probability did not exist, we could still get the same numbers using reliability theory. For our null hypothesis, the unreliability distribution, or the time to failure distribution, holds for the null hypothesis, which we have not rejected yet. And so we can generate several thousand time between failure samples, and we can generate this cumulative failure distribution where the MTBF here is our worldwide mean. So let's see what the time to failure is for let's go back to PV1. We will get a time to failure distribution that will equal this number using reliability theory, and we'll do the same using this number using reliability theory. So we need to either find a cell that has this correct relationship in it or create one. And there are 3 cells that have this correct relationship, where MTBF is the parameter mean. These 3 cells contain the right equation, so we'll use this cell. So we go to Excel Monte Carlo results, and we want to select that cell. This one has a correct relationship in it, and at the same time, let's select a cell that allows us to duplicate this PV2 number. So now for that one, we don't have an existing cell, so we use this blank column for ad hoc calculations, and I've entered what we need. We need the sum of 2 events that are drawn from our worldwide mean. And so I have the sum of these 2 TBE samples here. So this is the cell we want to reference. And even though this is only a 1,000 row distribution, for our purposes, we'll do both at the same time. And so let's refer to this cell. We hit enter, and then we'll hit F9, and we'll have our 2 distributions using reliability theory. We are working on the data tables now, and it will be a few seconds. After a few minutes, not a few seconds, these are our distributions. I've reformatted the x-axis and changed to a log scale because we want to examine the left-hand tail of the distributions. So for this first distribution, we're looking for 139,980. We want to know what is the probability of the worldwide fleet failing by that period of time. So we can go to 139,980, back to our distribution. We can come up and across and read it, but the better thing to do is to go to the column from which the data comes from, column D, and let's go down and find 139,980 and read the distribution that way. And so 139,980 is somewhere between these 2 values, so it's somewhere between these 2 values. Let's just select this one, and we will paste it back here somewhere for just reference, so we won't have to remember it. It compares, not so close to that, but if we increased the number of iterations, we would equal that number because of the underlying mathematics being the same, and we'll talk about that in a second. But let's go back and look at the distribution for the sum of two failures in a row. Look at that distribution, and there we're looking for from the worldwide fleet, what is the probability distribution for the time to the second crash, the two crashes in a row. That sums to 262,569. So if we come back to this distribution, which is not a good distribution, but for our purposes we'll use it, we'll see that we're almost off scale. The closest value we can find is the very first value. It'll be 1 out of 1,000. So we have a 1 in 1,000 chance of having two consecutive failures within the time that we did have our two consecutive failures. So these values that were arrived at using reliability theory is close to these Poisson values, and as we increase the Monte Carlo, the iterations, we would get closer and closer. If we took these two values here and plugged them into this equation, we would get exactly this number. So the mathematics are exactly the same, although the concepts are different. And I say independent because one would exist without the other. They're not dependent on one another. So let's copy this equation that's in PV1 at event 1. We place it here just so you can see it, and let's discuss it. Here is the probability of one or more events occurring within a look-back period of 1, when the mean is that at the event being under consideration, event 1. And that is identically equal to 1 minus the Poisson probability of 0 failures. And so this equation is what we want for PV1. Now for the Poisson, so this is 1 minus the Poisson probability of 0. Now when the event number is 0, the Poisson probability to the right, that part of the equation to the right of my cursor, reduces to a value of 1, so that the value to the left of my cursor is exactly equal to the cumulative failure distribution. So that's why the underlying mathematics are the same. So now let's look at so we, this cries out for a rejection of the null hypothesis. But let's look at one other consideration before we reject the null hypothesis. There's an additional reason why we need to reject the null. These p-values are based on the time between events being drawn from this population, if you will, or being like this population. And let's examine the fact that that's not exactly the case here, because this worldwide mean is based on mature aircraft with proven designs being in service. So this is mature aircraft. This is immature aircraft with unproven designs. So there's these p-values could be an upper bound on the probability that the plane is reliable relative to the worldwide mean. Again, these p-values are false positive. These p-values reflect the probability that the aircraft is as reliable as the worldwide mean. And so because this is a new fleet with an unproven design, let's look at what that means. In the 75-year history, starting with the DC-6, there have been several new design flaws that existed on new aircraft designs that were introduced into service while the flaw existed. And so they were introduced into service while unreliable, and the flaw was discovered in service. These slipped through the design and certification process. So if we looked at the last 10, including the 737 MAX, 3 out of those 10, and we will exclude the 737 MAX from the numerator because we are evaluating the MAX. So 3 out of the last 10, or 30%, have had a design flaw on the day that they were placed into service. So with that additional information, we should be suspicious that any new design, not just the 737 MAX, but any new design could have a design flaw. I think this is true for any engineered system that is placed into service. So, if there's some additional information such as this, we can use Bayesian thinking and apply that new information to our probability values. And we could even multiply these probability values by 0.7 in order to get perhaps a better estimate of the true probability of a false positive. So the point, though, I want to make is that we should be very sensitive to having design flaws in new systems. It's not all that unexpected. And so we should be sensitive to these probability values and be all the more willing to accept these probability values and accept the alternative: my new design is not as reliable as the worldwide fleet. Now we will, so we say that the fleet is unreliable relative to its peers, and we will see what the reliability is shortly. So this additional data can be applied using Bayesian thinking, if you will, to recognize that these p-values are really an upper bound. They may be much lower because of the simple fact that it's a new design. So we are going to reject the null hypothesis and accept the alternative hypothesis, and that is that the fleet is not as reliable as the worldwide fleet. So now let's look at the risk of continued operation if we don't ground the fleet after the second event. We did operate for 3 additional days before the fleet was grounded. And let's look at the risk associated with that. And to start with doing that, we have to replace our parameter for the worldwide mean with the MTBE after 2 events when we are drawing samples from a system with an unknown mean. So we have to go back to our process pump equations here. And so this is the average of the 2 samples. We can measure the risk of continued operation, but we are going to make our first assumption, conceptual assumption. So far, all of our assumptions have been with things like, for example, input data. We have calculated input data, but there are assumptions associated with that, because while the FAA and Boeing may have exact numbers, I know that they do, we have estimated numbers because those numbers, not all of them are published. So we've estimated from in various ways input data. Now, conceptually, though, we're about to make our first assumption. We are going to use this cumulative failure distribution and generate 10,000 samples that will form a probability distribution of the time to failure for our system that has an unknown mean. MTBF will be a random variable. It will be the MTBE after 2 samples of data. Now, up to now, lambda has been constant by definition because we've only applied this to our null hypothesis, which by definition has a constant lambda. Now we've rejected the null hypothesis and we're going to assume a constant lambda. Now, what is the basis for that assumption? Well, let's go back and look at history, for example. In all of these cases where we've discovered new design flaws in service, almost all have been a constant failure rate. There have been 2 that were an increasing failure rate. Now, if this should be an increasing failure rate, doesn't look like it's increasing, but if it is a decreasing failure rate, or if it is an increasing failure rate, then an assumption of a constant lambda will be a lower bound estimate on the increasing failure rate. There's been no case in the history of a decreasing failure rate, and I can't imagine there being one with a system in which the production process is continuously introducing new aircraft into the population. So the assumption of a constant failure rate, if it gives us a risk that is unacceptable, then it will certainly be unacceptable should the failure rate turn out to be increasing. So this is the basis for the constant failure rate assumption. And I think that it is good and reasonable and logical. So we're going to use this relationship. This relationship doesn't exist in any of these cells now. So we go to column A, that is for ad hoc calculations, and I've built this equation into this cell, drawing upon the MTBE as a random variable after 2 events. And so we can refer to this cell, I place this cell in the 1,000 row data table, this cell in the 10,000 row data table. I've already run the results, and this is the distribution for our MTBE after 2 events. We have a very wide distribution because we only have 2 events. If we had 200 events, this would be a very narrow distribution. But again, EIPA uses the data that exists because we don't want 100 events or even 10 events. We want 1 or 2 or 0 would be ideal. So we're after using the data that we've got, not trying to generate data so that failure data so that we can improve our narrow our distributions. We've got to use for things like aircraft crashes and other in-service failures of that type. We must learn to use the data that we have and not continue to think, well, we need to wait until we get more data. We have enough data. We just got to use it. So this is the distribution for the time to failure for the 737 MAX fleet after the second event. Now we have, let's see, we had by calculated estimate 3,396 departures during that 3-day period, or could have. We had some fleets, some planes that were grounded and I don't know how many. So this calculation is based on all the fleet flying, and I presume that the FAA and Boeing would assume that all the planes were flying if they decided to continue to operate. So let's look at 3396. We could come across and up and across and read, but again, it's better to go to column D and get that data. So let's go down and find 3396 or something close. Uh, 3396 this is pretty close. So let's just take this value, 0.0486. That's the probability of failure, or in our case, a third crash within that 3-day period. So let's go back up, and what we can do is paste this value here. This is the probability of failure. So we paste that value in. This is the consequence. Now the plane is either going to crash or not crash, and the number of fatalities are either going to be 0 or everyone on board, presumably. So for the consequence, though, we might take the average for the 2 crashes, and that's what the consequence of the issue is. When we multiply probability times consequence, that gives us risk, and here the risk is 8.4 fatalities, and so that 3-day delay should be considered as costing 8.4 fatalities. Now, you know, the true risk, there's either going to be 0 or 173, but this quantifies that risk in a way that we can manage it. To say that the risk is 0 or the risk is 173, both of those are wrong, and so this is the correct answer, and this, we should act as though those fatalities actually occurred. So that's the cost. So we were, in essence, unaware of the left-hand tail of this distribution. It was out of sight and therefore out of mind. Nobody would deliberately take this risk for a 3 days of operation. So we were playing Russian roulette, and we were unaware of it. As a matter of fact, if you go to the true risk of a game of Russian roulette is about 1 out of 6, or I think that's 0.167 about. So we could come across and down and measure the number of departures that we would have to go before we incurred a 1 in 6 chance of a crash. That number of days is, I looked at it, it's 12 point something days. So if that 3 days of delay had been extended, and it would have, but they extended it until they found some additional cause and effect data. And if that delay had turned into 2 weeks, then the risk of a third crash would have been exactly equal to or a little more than that of a real game of Russian roulette. So this kind of risk would not be undertaken knowingly, but we are undertaking that risk unknowingly because we are unaware of the long tail of this cumulative probability distribution. We've seen the benefit of analyzing crash event data because we can eliminate the risk of a third crash, and by analyzing contemporaneously upon the first event, we can eliminate the second event on the strength of probability values. Now let's look at the possibility that we can analyze precursor events that occur prior to this first event analyze precursors in order to eliminate even the first crash. And we, as it turns out, there are precursors that we can find that we can identify a unreliable aircraft before the first crash. So to do that, let's go to the final report of the investigation on the first crash that occurred October 29, 2018. Buried within this report is the beginning of a precursor. It's some of the data that we need to identify the precursor on page 169. This is a record of stick shaker activations on Boeing fleets during a period of time from 2001 through 2018. This data is here for a reason totally unrelated to a precursor. And I won't even get into that. But this data is some of the data that we will need. So we're going to take the model number and the total number of stick shaker activations. A stick shaker activation is like a warning system of an impending problem that where action needs to be taken. And so it's not important that we understand the event. It's just that this is a countable event over a continuum that we can measure. And we're going to measure, our continuum will be plane days in service. And every time we talk about analyzing events, I may have spoken about analyzing events in this video. Almost always, when I talk about analyzing events, I really mean event intervals. And so we're going to analyze stick shaker activation event intervals. We take this model number and the total number, we move that back to our workbook, and in a sheet called plane deliveries and interval calcs, we paste the data in or transpose the data from that crash investigation report into this gray section here. These are our Boeing types with all of Boeing at the bottom, and the number of stick shaker activations recorded in this period of time. And there's no direct indication of a precursor here, a precursor that can be a red flag or a warning of an impending catastrophic failure. The MAX, we only had one event, whereas the 737-800, we had 18 events. So if there's a problem anywhere, it would appear to be on the 800. But then we're going to get plane days in that interval. And we get that from downloading this data from the Boeing website, which includes, among other things, the delivery date for every plane by the model series. So this data has been captured by filtering using these filters, as well as if statements that are in column P. And so using all those filters, we extract these plane days within the interval. That allows us to get the mean plane days between the precursor events and the mean precursor for the interval. Okay, what is the mean within this interval from 2001 through 2018? This is the rate, the reciprocal of MDBE. The relative rate here normalized to the Boeing shows that the 737 MAX is about 31 times the Boeing average, and it is also head and shoulders above any other Boeing type. So this looks like the 737 MAX could be a precursor, and to analyze that with p-values, we're going to get our p-values in the conventional way, where we analyze a precursor event just like we did a crash event. Now, to get the plane days within the interval, we did assume a retirement age at 25 years. some of the fleets, some of the planes will retire prior to this interval, some will retire during the interval, some after the interval, and so that was considered. Now, when we look at the number of 737 MAX plane days to the precursor event, we can use filters that, if in the form of if formulas that are in column Q and R, to get to sum up all of the 737 MAX planes that are in this interval of time from being placed into service to the date of the precursor, which is the day prior to the fatal crash, which is 10/28/18, and then from there to the second precursor, which occurred the day of and on the flight of the fatal crash, the second fatal crash. So by using these filters, we get the two time between event data for our two precursor events. We had a precursor the day prior to the first fatal crash, and then we had a precursor on the fatal crash for the second precursor event. So these are the intervals, and this is the mean. We can move that data to our various data sets, and I've already placed that data here, so we can copy this data and move that to the probability amount and analyze it just like we have any of our other data. So we paste that in, and we do have p-values that are capable of rejecting the null. Now, let me explain one thing. These p-values are almost the same p-values as we had earlier, and that is by the magnitudes are by coincidence. This mean that we're measuring against is the mean Boeing stick shaker activation. It's the mean for the stick shaker activations. Now, what we had before was the mean fatal accident, the mean time or mean departures between fatal accidents for the worldwide fleet. So those things have nothing in common. So that if you see a similarity between these numbers in terms of magnitude and the ones that were there before, it's coincidence. Now the ratio of these numbers are almost the same. Or the ratio of the ratio of these numbers are almost the same, because they were basically occurred almost right on top of the fatal accidents. This was 1 day short of the accident rate, and this was on the day of the second accident. But the magnitude of the numbers is independent of what was there before. So we could reject the null hypothesis, and even without a consideration for the fact that we often have new designs in service that are unreliable when first placed into service. And so we should reject the null hypothesis and even take action on the basis of the precursor that was identified on the day prior to the fatal crash. Let's evaluate the p-values contemporaneously, line by line. When we had the first precursor, it generated a low p-value capable of rejecting the null hypothesis even before we consider that we could multiply that value by 0.7. And in this case, we would have had to eliminate the first failure. We would have had to respond within an hour or two or three, because this event occurred. There was a severe stick shaker activation on the day prior to the fatal crash. the issue was not corrected fully and completely the following night, and it was placed in service the next day. So that stick shaker activation continued, and we had the first crash. Now, so this stick shaker activation correlates very strongly with the crash event. That's why we don't have a very short opportunity to react. Let's look at the crash events again. This 737 MAX event was a severe stick shaker that I think lasted the entire duration of the flight. All of these others are severe stick shaker activations. There are many more stick shaker activations on the Boeing fleet than reported here. So these are serious, severe activations, perhaps measured in terms of duration of the event, because many of these returned to the airport, some diverted to other airports. So it's obviously a severe activation problem. And so there's a strong correlation between the precursor and the crash. For the MAX, it's essentially a 1-to-1 correlation. It's one precursor equals one crash. And that is why the short window of opportunity to respond. So even with automation, it may be hard to respond within that period of time. By automation, I'm talking about automating the analysis methodology. But if the plane had been repaired properly, that first crash would not have occurred the next day. And that first crash would have been pushed off into the future. And indeed, event 2 would probably have been our first crash had we repaired the plane properly back here. So event 2 would have been our first crash, and so we would have had about a 4.5 month period of time to respond and react to this low precursor. Now, likewise, the crash that occurred, event 2, did not necessarily have to crash. We had a strong stick shaker activation, but the crew could have some way perhaps overcome that. And the first crash could have been pushed off into the future. But these precursors remain. So as we conceivably overcome the crash event through maintenance or through skilled flying, we could have had these precursors before the first crash. So in this case, the precursor was so strong that the precursors and the crashes are almost instantaneously together. But in general, we have a response time to be able to respond to these precursors. Now, another thing, we have one situation here, precursors, that we are automating. That is just one of hundreds of situations that we have to monitor. Because this time we have a flight control problem. The next time we have a new design, it might be or the next problem that shows up might be a landing gear problem. Who knows? Because we're using automated data analysis here, looking for signals that there may be a design flaw in our system. Not a specific design flaw, but design flaws in general. So we have to have hundreds of precursors that we're looking at. Now that sounds like a lot of work, but once we set this up, it's automatic. And we aren't aware that any analysis is going on until the system, the automated data analysis system, generates precursors that draw our attention to something that is perhaps worthy of looking at on the basis of these low p-values. This table is for 4 aircraft types and 5 different design flaws that were discovered in service. Each one of these design flaws had 2 primary events each. Now, for the 787 battery thermal runaway, there was an event that occurred on the ground and not in service, and I consider that a primary event. So with that understanding, all the others were crashes or emergency landings. The FAA and predecessor organizations failed to make the right decision or take the right action upon the first primary event. Therefore, a second primary event was required to draw attention to what eventually turned out to be a design flaw. Now, EIPA failed to recognize the first primary event upon the fire issue on the DC-6 in 1947. EIPA required the second event before it had a p-value sufficiently low to reject the null hypothesis. On the other 4 occasions, the unreliability of the aircraft relative to its peers was recognized upon the first event. So there were 10 decisions with EIPA, if you will, on these 5 design flaws. The first one was a false negative in 1947. The other 9 were true positives. And in all of the applications of EIPA to aircraft types and design flaws discovered in service, these and others, there have never been an occasion where EIPA showed a false positives. So for this data, 9 true positives and 1 false negative. So this is why I think the FAA and the commercial aviation industry should apply EIPA starting immediately. I want us to understand that what we are doing is analyzing not events, but event intervals, the intervals between events. And what we're doing by way of p-values is identifying intervals that lie outside a reasonable expectation. A reasonable expectation as defined with probability values. So they flag us of events that are too short or too long relative to what we should expect in our range. And the events do not have to be equipment failures or aircraft crashes or something of that nature. In looking at this video, I'm concerned that perhaps you may think that it is applicable to equipment issues only. But let's look at this situation. Derek Chauvin pled guilty in a trial related to George Floyd's death just a few months ago. And in pleading guilty, he also pled guilty to excessive force used on a 14-year-old boy, black boy, where he held his knee on his neck and hit him over his head with a flashlight to the point that it required stitches. Now, what would Derek Chauvin's probability table look like? Wouldn't there be sales of red? Especially if we go back and look at all the primary events. Were there not precursors that would show up on a probability map? I would suspect yes. And so in an era of big data, why couldn't we apply it to events of excessive police force for individual policemen on the street and individual departments? So this is quite doable, especially in the era of big data. And so EIPA has application in areas far greater than just equipment failure, I believe. So this series of, there's going to be a series of videos that will comprise a tutorial on the EIPA. There's a lot of applications and analysis methods that haven't been demonstrated. And so this series of videos will form something of a tutorial, as well as a how to use the probability map that is part of the method. And so this series of videos the links will be placed on the PMF series website as the videos become available.